Hello, I'm back with another couple of circuit questions. We're starting here with a cell is a source of EMF. When the cell is connected into a circuit, the potential difference measured between its terminals is called the terminal PD. Is less than the EMF. Right, so we're going to be looking at internal resistance here. Starting off with a definition. So define the term EMF. These are the sort of things that tend to catch people out because they don't practice their definitions enough. If you get stuck with definitions, start with the unit of saying what the unit is. So we know EMF is in volts, so we want to say something about energy per unit charge because that's what voltage is. So energy per unit charge, and then in what situation, what are we doing with that energy per unit charge? So it's the energy per unit charge transferred, because that's what we're doing with energy. We transfer it from one place to another from the source. So, we're saying the cell is a source, so we use that energy per unit charge transferred from a source. And where's it transferred to? To an electrical current. So it's just putting together our terminology in a, this is what the thing is we're dealing with. We're dealing with some voltage. The voltage is energy per unit charge. What are we doing with that energy? We're moving it from a source to an electrical current. So yeah, that one does tend to catch people out when you have those EMF definitions. All right, explain why the terminal PD is less than the EMF. Well, we've got a PD across the internal resistance. So the terminal PD, and we can quote the formula here. So that's V is going to be equal to our EMF minus the current times the internal resistance. So that's what's happening here. So we've got, so put in like IE, we've got energy lost to energy or voltage, and therefore voltage. So energy, voltage lost to internal resistance. So yeah, if you're going to put that formula in, then you can say, okay, the terminal PdV is equal to that's the EMF. So say, where that E is equal to the EMF, I is the current, and R is the internal resistance. So define your letters if you're going to write the formula in. I won't write out each one of them, but just underneath you can just put, what each one of them is, just so you've got the whole thing there. So you're putting it in words and you're putting it into a formula. In the circuit of figure 3.1, the cell EMF 1.6 volts, so put that in the picture, internal resistance R in the picture, current 0.2, yeah, all this stuff is in the picture, right? They haven't put the 1.2 volts across, well, the terminal PD is also the PD across the whole of the circuit. You can look at it either way. This voltmeter that we put in here, what is it measuring? Is it measuring the potential difference across the resistor, as in that is the rest of the circuit, or is it measuring the potential difference across the cell? Well, it's measuring both. So it doesn't really matter which way we look at it. Calculate the values of the resistance big R. So that is going to be equal to the PD across it divided by the current. So that's 1.2 volts divided by 0.2 amps. So that's 6 ohms. What's the internal resistance little r? Well, we've got a quarter of the voltage is across the internal resistance, so we must have a quarter of the resistance, so it's got to be 2 ohms, so we got 2 out of 8. Of course, you could just do it again. You could do the calculation of saying, well, that's 0.4 volts, which is the remaining voltage, as in it's the EMF minus the 1.2 to give us the 0.4 divided by the same current, because it's all in series, which is also giving us 2 ohms. So it doesn't matter whether we do a V equals IR calculation or whether we just divide up our EMF in proportion to the resistances. It's the same thing. Part C, the current in the resistor remains constant at 0.2 amps for several hours. Calculate the charge which passes through the resistor in 1.5 hours. Right, so that's our Q equals IT on that. So we've got, was it 1.5 hours? So 1.5 times 60 minutes times 60 seconds times 0.2. So we're going to have 0.2 times 1.5 times 60 is going to give us 18, isn't it? So we've got 18 times 60, which is 600 plus 480, so 1080 coulombs. All of this is two significant figures, so we go 1100 coulombs to two significant figures. The energy dissipated by the resistor in 1.5 hours. So the energy, remember the voltage is joules per coulomb. So if we take the voltage multiplied by the coulombs, then we're going to get the energy. That's what we're going to have on there. With slightly unconventional letters I've put there, but still we're multiplying this number of coulombs by the voltage. So, and the voltage was what, 1.2. So we've got 1.2 times 1080. So we need to add a fifth on, which is an extra 216. So that is going to be 1296 joules, which is 1300 joules, again to two significant figures. So giving us some quite nice numbers there, keeping us off the calculator. At the end of the question, no, we got the last bit. Right, the cell is left connected to the resistor for 12 hours. The graph shows the variation of current with time. Describe how the current varies with time and suggest reasons why it varies in this way. Right, this is another one that people don't answer the question fully, so they don't get the full marks. So what you're going to want to do here, we've got to do a describe with reasons. So we're going to want to split this up into sections on the graph. So we can say that we've got a constant current of 0.2 amps for first sort of 9 hours. Seems to be around about 9 where it starts to taper off. So that's one zone. You could then say we've got a sudden drop. Well, we've got a sort of gradual drop of 9 to 10 hours, and then a very sudden drop from 10 to 11 hours down to zero current. So that's just describing the variation with time, but now we want to suggest reasons for why this is happening. So for each one of these areas that we've identified, each one of these domains on the graph, we want to have a reason. So why have we got a constant current for the first 9 hours? I mean, what is determining our current on all of this? Well, we're going to need to have constant cell properties. So we can say that this constant current is because we've got a constant EMF and internal resistance. So of course we can write those out in words, but if our EMF and our internal resistance haven't changed, then we're going to get the same current coming out of the cell. So what's happening then when it starts to drop off? We know with cells it's going to have something to do with its running out of energy. So we can talk about it in those terms. So we can say that the chemical processes in the cell start to decrease. In cell, decrease. Therefore, EMF starts to drop. Therefore, current starts to drop. So we can have that. And then for the last bit, we can say the same thing. And we can say that these chemical processes are decreasing more rapidly, so down much quicker. Therefore, the EMF goes down much quicker. Therefore, the current goes down much quicker. So you can just translate that into actual words. But the key thing here is you've identified 3 sections in the graph, although you could probably get away with just doing 2. But, you know, let's be thorough. We've got 3 sections on here. And then for each section, you're saying why that section is behaving as it is. You want to have the full lot there. That's how you're getting full marks from the mark scheme. Don't just have, oh yeah, well, it's constant and it drops off. without trying to quantify it in some way. You know, you want to actually put in some time periods in all of that, and then for each section give a reason. Otherwise you haven't got a complete answer, and that's where people fall down on those sort of questions. Right, so onwards. Resistor X constructed from a rod, cross-sectional area that, length that, resistivity that. Yeah, okay, fair enough. Everything they've given us in that picture plus that resistivity. Show the resistance is 3.2 kilo ohms. Right, so our resistance is the resistivity times the length divided by the cross-sectional area. So 2.4 times 0.012 divided by 9 times 10 to the minus 6. Right, they've given us some really nice numbers there in all of that. So let's tidy this up a bit. So we've got 24 times 12 over 9 times, that would be a 10 to the minus 4 at the top. So by the time we dealt with the minus 6, it would be times 100. So we can take a 3 out of each one of those things at the top and have 8 times 4, which gives us 32 times 100, so 3,200 ohms, which is what they wanted. The power rating of resistor X is that's an 1/8 of a watt. Show that the maximum potential difference which should be applied safely across the resistor is 20 volts. So we want to have our power in terms of volts. So volts, this is our V squared over R. I'm just going to rearrange. So we're going to have the square root of P times R. So that is the square root of an 1/8. I've written a half, an 1/8 times 3,200 square rooted. So 32 over 8 is 4. So we're going to have the square root of 400, which is 20 volts. So again, nice numbers. Student needs a resistor of the same resistance as X, but with a larger power rating. Right, 4 times the power rating. Only resistors available are identical to X, so you could put them into that combination of resistors is what's suggested. Potential difference across the combination is now 40 volts. Show that the total resistance of the combination is 3.2 kilo ohms. Okay, right, well, this is going to be, you know, straightforward enough dealing with all of this, because I mean you can factorize out. Let's just deal with this in terms of X. Yeah, these are, you might just be able to see this straight off, but essentially we're putting 2x and 2x. So we're going to have 1 over 2x plus 1 over 2x 1 over. That's going to be our total resistance. You don't have to bother putting the 3,200 in. I mean, you can do if you're just going to stick it into the calculator, but clearly we got here 2 over 2x, which is 1 over x, and the reciprocal of, which equals x, and x is 3,200. We're used to these things. If you've got identical branches on a resistor network, then you're just halving the resistance. So we're going to have 2x in each one, and then you halve them when you put it in parallel, and you end up back where you started. So easy enough there. Show that the power dissipation in each resistor is 0.125 watts. Right, well, this is what we just had before. This is this calculation. We've still got 20 volts across each of the resistors, so we're going to end up with the same thing. We're just doing a V squared over R. So we're going to have 20 squared over 3200, which is 400 over that. So that's 4 over 32, which is 1 over 8 watts. So same calculation. A bit weird that they've done that. But hey ho. Another resistor Y is constructed from the same material, twice the length, twice the diameter. Show the resistance is half. So resistance rho L over A. So we've got L is times 2. We've got the diameter is times 2. Therefore, area is times 4. So we're going to have, therefore, the resistance is multiplied by 2 and then multiplied by 1/4, which is R over 2. So we're just going through in those steps. I mean, you can, if you're wondering how you'd actually set that out, I suppose, in the answer, you could say that R Y is going to be equal to, actually start putting these things in. We can say that we've got rho times 2L divided by 4A, and then you can say rho L over A is equal to Rx. Now going off the original equation, so then we've got Rx over 2. So you can set it out like that is probably a safe way of writing it out as an exam answer. That's the way people would tend to talk through it. Whether you'd get away with that as an answer, I don't know, maybe, but it's probably safer putting it into something like this, actually using the formula, put in that definition of what Rx is, and then just modify everything around that. Two resistors X and Y, where we've got this new resistor. I just put Rx and Ry in series of each other. State and explain which resistor dissipates the greater power. So we've got the same current for each one of them. So the power is proportional to R. So we're going to have greater P in Rx because Rx is greater than Ry. So there we go. It's a nice rounding off on that. It was quite an easy second question. The first one I think was a bit more interesting because of that descriptive section in it. But yeah, I'll just do the 2 in this one.